Yo, what up? Welcome to Made by Ozzy. I'm Ozzy. And this is episode 2 of my crypto series where we're going to continue building a Bitcoin slash Digibyte miner out of Python. And so all of the Python scripts we're going to write today are already up on the GitHub. So the link for that is in the description below. You could go sync up with that right now. In the last video, we went over the specific data that you need to pump through a hashing algorithm, and what it is, what it does, right? So if you haven't seen that video, go check it out. I'm going to try and put a link up there, but otherwise it's just the previous one in this playlist. So today we're going to build a few test benches in Python. First one, we're going to build one just to test SHA256 to make sure that we actually are running the hashing algorithm correctly and we're getting the responses we expect. The second one is to actually test a known block, which has already been mined on the blockchain and everything. It's a public ledger, right? So we could go just look at it and make sure that we could reproduce the same results. And then the last one is we're going to make it so that it's sort of, if assuming we didn't know a nonce, to try and find a nonce. And if we pump in this good block that we're going to get off the blockchain, then we know it should give us a nonce. And so this is going to be our test benches. So let's go ahead and get started. In order to test SHA-256, first thing we need is a control, right? We need to know an expected output. So here's a little online calculator. I got the link for this in the description. And if there's no input at all to SHA-256, we should expect this output. Okay, so let's try and write a little Python script to see if we can get that output. And so this is the Python project. I'm going to go ahead and make a new file, new Python file. Let's call this SHA256 Testbench. We're not going to write the SHA256 algorithm from scratch, not yet at least. We're going to have to in order to put it on the FPGA in the future. But for now, we're just going to use a Python library. So we're actually going to depend on using this library here, hashlib, or hashlib, whatever. It has the SHA256 algorithm built in. So let's go ahead and import that in our Py script here. Import hashlib. And I guess that's just built in because PyCharm doesn't make me install it here. You can look through the documentation, but it's as simple as it's going to return a hash object, which has some information, and we're going to use that. So it's going to return a hash object. And that equals, we're going to use the hashlib library, we're going to use the algorithm SHA256, and we're not going to give it anything. It's an empty input. And what we actually want out of it is this resulting string. And we're going to get that using the digest hex. Let's see. This is why I have the documentation open, right? We are going to use this hex digest method to get that. So we want this, the hex digest equals hash object, which is what got returned to us from this method call. And we're going to look for the hex digest. And let's just print that out. Hex digest. Okay, let's hit run and see what we get. Run. And that's great. Look, E3B0, E3B0, and last one is 2B855, 2B855. Great. Okay, but to test this properly, let's do one other test. So let's just put in a number 1 here and hash it, and here's a different string. And if I try and do that here, I actually will hit a runtime error because this method SHA256 does not expect an int input like this. I need to provide it something in a byte format. And actually this here is when it reads into 1, it's reading in the ASCII character 1. So I need to convert the ASCII character 1 into a byte format. And in order to do that, I am going to use another Python library, codecs. This is just a convenient way to kind of turn ASCII into bytes. So let's go ahead and import codecs. And here that's going to, let me call this message codecs encode, and I'm going to give it the ASCII character 1. No. And then I'm going to pass message into here. And that should give me the output that I expect. Okay, 6B86B, 6B86B, and the last one, 5B4B. 5B, 4B. Okay, great. Cool. Okay, so that verifies the SHA-256 algorithm by itself, but we need to actually take a We want to verify an entire block header, right? We want to make sure that we can get all the data, put it together, and when we run it through SHA256, we get the output that we expect. So let's go find a sample block. We'll just copy one. We're going to go use a blockchain explorer. And there are plenty of blockchain explorers on the internet, but this one works fine. Chains.cryptoid. It's got a good one for Digibyte. And Digibyte has 5 mining algorithms, so we need one that was mined specifically with SHA256. And this one was here, this 118.33.445. And we could actually check the raw block here to get all of the information we need. Like we have the previous block hash, we have the Merkle root, we have the bits, and the what is it? Version and the timestamp somewhere, time, and then it also has the nonce that was used. So we could use this as our test bench. To make sure that we could actually, hash a block correctly. But we don't have to, trust this website. Let's go ahead and verify it with our own full node. So I got the full node running here, and you could check the last video to see, examples of that. And what do I want to do? I want to check that this block is accurate. So I'm going to reference the Bitcoin developer documentation, and I'm going to use this method, getblock, in here. So I need to provide a block hash. So I'm going to come over here and provide it this hash, copy and paste that, which is what it was up here, right? And I'm going to go ahead and use this little executable here, Digibyte cli for Digibyte client, Digibyte cli, get block, and then in quotation marks, provide that hash, and it should give me all of that information. So let's verify this. And see what we got. Previous block hash is 8DA53, 8DA53, 1862, 1862. Nice. And notice I'm only verifying the first and last ones. It's usually enough. Merkle root F5F, F5F, 44, 44. Great. All right. Time 16044, 16044, 59159, 59159. Great. The nonce 31626, 31626. Everything's looking great. All right. We verified with our own full node. Okay, so let's make a new Python script here, new Python file, and let's call this one block header test bench, because this is where we're going to try and actually hash everything. So let's import the things we need. We need the hash lib, and then we're going to use codecs is what again. So let's do that. Okay, so we got our imported stuff, and let's specify what we need. So what do we actually need? We need the version, previous hash, Merkle root, timestamp, and bits, and nonce. So let's start with the version. Version is just this number, Control C, version equals Control V to paste. Okay, next one was the previous hash, which is right here. It's this long hexadecimal number, so I'm gonna save it as a string here, and you'll see why in a sec. And then I have another hash. I have the Merkle root hash. Going to save that as a string here as well. Merkle, should spell Merkle correctly. Okay. And then I need the n bits. Actually I need the time first. So time is just that number right there. So let's call this T for time. And then I need not the nonce, the bits. And the bits is a short hexadecimal number, so I'm just going to hard declare it like that. And the last thing is the nonce. Oh, I need an equal sign there, don't I? Okay, and the nonce equals that. Okay, so I got this mix of numbers and strings. Now, how do I actually format this into one cohesive message that I'm going to feed into this, this SHA256 thing. SHA256 message. Or you know what? Actually, I'm going to call this header, right? Because that's more appropriate. We're constructing the header. This is the block header. That's what we're going to pass in. And that's hashlib, not haslib. But what is this, right? Okay, so what's this going to look like? So let's reference the documentation here. Again, the Bitcoin developer documentation. And it does describe. So I mean, I'm gonna save you some debugging because I had to play around with this a lot. It is the hashes are an internal byte order, whatever that means, and the other values are all in little endian order. And little endian makes sense. That's just the least significant bytes go before the most significant bytes. This one I had to play around with internal byte order. So I'll show you how we did that right now. First, we're going to need one more Python library, struct. We're going to use this to format numbers in little endian order. So let's go ahead and import that into this project or into this Python script as well. Import struct. Okay. And what we need to do is construct a message that's going to be several things basically all put together. So first things first, let's do the version. So the version needs to be in little endian order. And the syntax for that is going to be, we're going to use the pack method inside of that struct library. So struct.pack. We're going to define little endian, and you do that with this little underscore, or I'm sorry, less than L. And now we just give it the number we want, version. Okay, great. And then we're going to add the next things, which is going to be previous hash. So the next thing is the previous hash. And that is a string, right? So I'm going to use the codecs library to decode that string. So I'm going to tell it the string previous hash, and it's going to decode it as hex because the string is all hex. I don't want the byte representation of the ASCII values. I want it to read this as a byte, as hexadecimal values, and give me the bytes of that. Now, this little tidbit, internal byte order. What that means is the bytes need to stay in the order that they're in, and a byte is 2 hexadecimal characters, but reversed. So here, this previous hash, it gives you this, this is like the most significant byte all the way on the left. You actually want the least significant byte all the way on the left, but this can't be reversed. So you can't just flip the whole string around. It's every other. These two need to stay in the correct order, but they need to be at the end. You could do that by actually flipping the byte array around instead of flipping the string array. So this codecs.decode turns it into a byte array. And now to flip that around, syntax is just : 1, or I'm sorry, -1. And that will just flip the whole array around. Okay, what is the little error I'm getting here? Oh, I guess I have to capture all this in a parenthesis. Okay, but I'm not done yet, actually, so I'll do that when I'm all done. Plus, and then I need to do the same thing I did here with the previous hash. I need to do it with the Merkle root, so I'm going to copy paste that and just change this to the Merkle root, because like the documentation says, the hashes are an internal byte order. And I have 2 hashes I'm working with, the hash from the previous block header and the hash from the Merkle root. Now I have a few other things, right? I have the time, bits, and nonce, all of which are just packed as little endian. So let's just do that. Struct.pack, little L, it's a big L actually, but T, okay, and I guess I could just copy paste this because they're all going to be more or less the same. I'm going to go ahead and close that off right there. So instead of T, it's going to be bits, and then nonce. Okay, so that should handle the header. Now, how to actually hash it. So it's as simple as this, right? But except I'm not actually returning a digest. Now I'm returning a digest. But this isn't exactly what I want, because you actually have to hash it twice. That's just part of the protocol. It's part of the proof of work protocol. You have to hash the header twice. So the actual digest we want is the result of doing it twice. So there it is, doing the first time. I hashed the header the first time. Now what I'm going to do is I'm going to hash the output of that, which is the digest. 256 digest dot, but this time I'm going to return the hex digest because I don't actually want the bytes. I want the ASCII representation, so I could print it and we could see what we get. Okay, so just go ahead and run this. And bam, that, a lot of zeros is pretty promising. So I got BACF and a bunch of zeros. And well, so see, I actually got it backwards. I got all the zeros here on the left. And so I got BACF, but this is CFBA. And that's what I was trying to say by how, it's going to be 8D, the 8D will stay in the same order, but the 8D will appear on the back end here. So if I actually wanted to see the hash represented how it's shown here, what I would have to do is I'd have to reverse the array of bytes directly. So not the hex digest, I'd have to reverse the digest. And so notice they're different outputs here. So I could still get that because of how I did the naming right here. So let's call this reversed digest equals hashlib dot SHA256 digest dot digest. And I'm gonna go ahead and reverse it with that little syntax. Okay. And now what I can do is that's bytes, and I want to print it as ASCII, so I could use this codecs library, codecs, and I'm gonna encode bytes, not decode. And I'm gonna encode that reversed digest as hex. Okay, let's run that. See what we get. And there we go. Bunch of zeros and CFPA. Bunch of zeros, CFPA. Great. Okay, so that verifies that we are actually calculating, or we're actually, putting together all the information correctly. But this isn't exactly what we want, right? We actually want something where we have these first 5 things and we're guessing for a nonce. So let's expand this test bench here to do exactly that. So what we want to do is, well, first things first, actually, we need to figure out what we're looking for. So what we have is this bits number, right? And we need to somehow turn that into a difficulty for which this output here, this digest that we get from this, will be, lower than. So this is only, a few bits, and this digest is definitely, we could see that this is a lot bigger than just those 8 bits, or those 8 bytes, I should say. So how do we turn that into it? So again, we're going to reference the documentation, and this is how we can transform that 8-byte n bits number into a 256-bit unsigned integer that represents a difficulty. And it's pretty simple, actually, straightforward. What we have to do is we have to split it up. The 3 least significant bytes, so the rightmost 6 hex characters, are going to make up the mantissa, and the most significant byte, the leftmost 2 hex characters, make up the exponent. And this is how it's sort of mimicking a floating point number, which is made up of a mantissa and an exponent, which is very similar to scientific notation that you may have seen. It's 10 raised to the 2 power or something. And so this is actually pretty easy. If we split up that n bits into the mantissa and exponent, we could actually just left shift over the mantissa by a certain number of bytes, which is defined by the exponent. So let's split it up. So if we want to get the exponent, we want the topmost byte. What we can do is, that's defined here, exponent equals, and what we have is this n bits, right? So assume we have just bits that we're working with, and we want the topmost byte. So what we can do is we could mask it with what we want. We want the topmost and then nothing else. But you know what? This isn't exactly right, actually, because this is gonna leave it in the place that we need. We don't want it in that. We actually just want this, but like for all these to just go away. So we're actually gonna right shift it to get rid of those 3 bytes. So if I want to get rid of 3 bytes, I need to right shift by 3 times 824 bits. So right shift. Okay. But the masking will work for the mantissa, so let's do that. So bits, and I want just the bottom 3 bytes, so I'm going to ignore the first byte, and there's 2 for the second one, 2 for the third, 2 for the fourth. Okay, that should give me the bottom 3 bytes. And now what do I want? I just need to take the mantissa, and I need to shift it over by this by this many bits. I'm gonna have or by this many bytes, actually, I should say. Whatever I have in the exponent, I'm gonna subtract 3, and that's how many bytes I'm gonna shift it over. So I could have my diff is going to be equal to my mantissa is just going to be shifted over by however many bytes I have in the exponent minus 3. But remember, this is bytes, and the shift operator works on bits, so I need to multiply all this by 8. And for good measure, I'm actually going to capture all this in parentheses, make sure I don't start missing things. Okay, so that's going to shift it over by that much, and that should be my difficulty. And that's more or less it. So for a sanity check, I know that this one, should be good, right? Because we checked the output. So that means that this digest, it's actually the reverse digest, because again, the ordering in this in Bitcoin Core and Digibyte Core is sort of funky. So it's reversed here, so that's very important. So we already got this reverse digest, but this reversed digest should be less than this difficulty that we just calculated. So let's see if that's true. This should just print true. So let's go ahead and run this. Oh, and I got nothing. Oh, it's because, okay, it's because I'm comparing it directly to an int. So if I want to compare it directly to this, I have to transform, this reverse digest is a form of an array of bytes, but my diff here is an integer. So I just need to look at that as bytes. So I can use this little method, 2 bytes. And I have to tell it how many bytes, and it's supposed to be a 256-bit integer. So 256 divided by 8 is 32. It's 32 bytes, and it is in big endian format. Okay, now this should work. Okay, true, good. Okay, so now I need to build a loop to check every nonce, and I'm gonna import one more library. I'm gonna import time so I could actually keep track of the time. Okay, so let's predefine nonce to be 0, and we're going to do a while loop while nonce is less than the max nonce, which is, it's 8 f's, right? That's the max nonce, so it's while it's less than or equal to that, then colon. And then what's it going to do is we have to reconstruct this exact same header that we constructed up here. So let's go ahead and reconstruct that. Okay, and then we have to take the digest of it. So let's get the first digest. Digest equals hashlib.SHA256, and we're going to pass in that header, and we're going to request the digest out. Okay, and then we got to do it again, right? So let's call this, go ahead and steal that name, reversed digest, because we're going to go ahead and run it through the same algorithm, SHA256. We're going to run the previous digest through that, going to get the digest out from that, and then we're going to flip it. And that's why it's called reversed digest. Okay, and you know what? So we actually want this, this difficulty. I'm going to need this difficulty, but I want this value here. So let's do diff in bytes, and we're going to steal it here. Control C, or pre-compute it. I just want it to be pre-computed, because what I want to do now down here is compare, right? If reverse digest is less than this guy, difficulty in bytes, then I'm going to go ahead and print the nonce and just print success and break the loop right there. Break. And then gotta increment the nonce, plus equal 1. Okay. And I want to do a little bit of timing, so I imported that time. So let's keep track of time. So let's call this start time, and it's just going to be time.time. Okay. And down here, I don't want to interrupt it too often with timing, so I'm going to do a little conditional if nonce value, let's take the mod, let's do every 100 values. So if the mod of the nonce mod 100 is equal to 0, and skip the first one. I don't want to look at if, and nonce must also be greater than 0. I don't want to worry about the first one. Then let's get a new time. Cur time equals time.time. Okay, and find the time difference. So time diff equals cur time minus start time. Okay, and now let's calculate hashes per second, which is pretty easy. It's just our current nonce divided by time diff. And let's go ahead and print all this. So print nonce %d to show a decimal, tab character, and then let's show hashes per second. Let's do it as a %f to show it as a float. Okay, and let's feed in the values we need. So we need the nonce and we need the hashes per second. Okay, that should do it. Okay, let's hit run. Okay, that's actually a lot better than I thought it was going to be. Something like 100K hashes per second. That's pretty respectable for CPU only. I'm kind of surprised by that. So this should take this will take a few seconds, maybe a few minutes to actually get all the way up to that nonce. So let's see how long that takes. So I did the math and it was going to take something like 45 minutes. So I cheated a bit and I went back and I changed the nonce to just a little bit lower than what I knew the nonce should be. And so ignore these hashes per second. That's just nonsense because of how it's calculated. But check it out. It successfully stopped on the correct nonce. 31. This is what we were expecting to find, and this is what we found. So great. All right, dope. We were able to get everything working. SHA256, check. Block header, putting everything together, verifying its output, check. Little script to make sure that we could search for a nonce and actually get a good one out, check. Everything's going good. So on the next video, what we're going to do is we're going to actually build the communication over to a mining pool. So we could, instead of having to look up on a blockchain explorer, you know, version and previous hash and all that stuff, we are going to request that information from a pool using it's going to be a normal TCP/IP connection. We're going to open like a socket and we're going to send strings to this pool formatted as a JSON struct or packet. I don't know what the term is for JSON, but it's going to be the JSON information sent over is going to be per the Stratum protocol. And I was hoping to make this whole series only just the 3 videos, the last one, this one, and then Stratum after. I think it's going to be 2 more. So in the next one, I'll probably make a test bench just for Stratum. And then in the video after that, we'll probably marry everything together. So it's one cohesive miner. But anyway, I hope you enjoyed this video. Make sure you hit like and subscribe so you don't miss out any of the videos. If you're trying this at home, if you're having any trouble, please leave me a comment. I've gotten a bit of feedback from a few different viewers, and I'll be honest, I got a kick out of it. I think there's not a whole lot of people in the world that are doing really neat engineering things, and I really like hearing about it when other people are doing, either you're doing this project that, on this channel, what else you're doing, what problems you run into. This stuff is interesting. So leave a like, hit subscribe, leave a comment down below, and I really hope I see you guys next time.